Yeah, thanks for that super nice introduction. So today I'm going to talk about things that I've been thinking about, things that I think are important going forward. Mostly having to do with what we can do with reward models at Inference-time in modern language modeling. So as most of you are familiar with, modern language models are extremely powerful technologies, and they've been dictating how we interact with the world, how we do science, how we do computer science and so on. And they have had enormous empirical success with commercial applications, applications such as math and the physical sciences. But with all of this success, we still have a very limited fundamental understanding of how we work with these models. In particular, we don't really understand how to do training, how to think about safety, and how to do reasoning with these models. So a part of this talk was trying to sort of explore how to do reasoning and how to sample from these models. Okay, so broadly, the reasoning in LLMs correspond to trying to understand how we can elicit complex reasoning behaviors from these trained models. And these involve like multiple steps of reasoning, multiple steps of checking, and multiple long horizon of interacting with these models. So the applications are that they have been used for so far is mathematics, coding, scientific discovery, and in fact even for understanding applications such as AI alignment. Okay, so broadly speaking, we'll think about this in somewhat of an abstract way and try to see how we can design algorithms in this framework. Okay, so that we are all on the same page, the way I'll think about language models is really as a setting where you take as input tokens, and given these tokens, it gives you a conditional probability distribution for the next token conditioned on the tokens that are given as input. And the way I'll abstract away trying to elicit new behaviors or new complex behaviors from these models is to try to think about how we can sample from a new distribution that is different from the original distribution that you started with. And I'll think of this as some sort of a reward function that is a function of the output that you are desiring. So I'll refer to this as a tau, and again, you should just think of this as some sort of reward model. And this sort of abstracts many other settings that you might be familiar with. In particular, like everyone here is like super familiar with how we think about reward modeling in the context of reinforcement learning with human feedback, where you want to think of the star function as some exponential of some reward model that you have learned. It also abstracts things such as constraint sampling, where you want to only output solutions that you consider to be valid or safe. For example, you only want to output programs that compile under your favorite compiler. Turns out this also captures some other fundamental problems such as posterior sampling and inverse linear problems in, say, image reconstruction. This turns out like problems like image recovery also have the same form as the form that we have looked at before. So at an abstract level, this is a super important primitive to understand how given a probability distribution and a target reward model, how we can try to understand how to sample from these objectives. Okay, so this is for the rest of the talk, I'll aim to try to understand how we can sample from p tilde given access to p and tau, and try to understand how we can solve this problem. Also feel free to ask questions at any point. I'm happy to stop. Okay, so this is my abstraction of how I'll think about eliciting new behaviors from models, because the starting model p is the model that you started with, and tau sort of tries to indicate new behaviors that you want to see from models. And if you think about this for a few minutes, you can come up with many ways you can solve this problem. Maybe the most sort of first problem you think of, solution you think about is just to retrain this model on new data and maybe new architecture. I'll refer to this as pre-training. So basically, like roughly, you can go out, collect more data, and maybe just try to train a new model to get the behaviors that you want. The second solution to this problem, which is maybe perhaps more popular, is something I'll call post-training. It just means that maybe you go collect some new data, collect some new verifiers, go find some labelers, and then you post-train or run reinforcement learning from the model that you already have on the new target distribution that you care about. And the third solution, which is becoming more and more popular, is interventions at sampling time, where you look at the model, a fully trained model, and try to change the behavior of the model by interfering with the sampling distributions and try to understand how we can guide our models towards solutions that we care about. The majority of the talk is going to be about the third solution to the problem, but we'll quickly look at the post-training thing, so because we are just more familiar with this. One way to sort of think about this problem, this solution to the problem, is like reinforcement learning, and this picture tells us how typically these loops are run, where you set up an environment and you have an agent, which again in our settings are like language models, and using a reward model will guide our agent to do better on the environments that we care about, and repeat this for every environment that we perhaps care about. So this is like a quick summary of how modern reinforcement learning frameworks work in training. I mean, this has been fairly successful, and this is part of the reason why we have Claude and like GPT and so on. It indicates that like this framework is really successful. The only problem is that this is super expensive to run, and it takes a huge amount of effort, and can't be done each time. You need to sort of get a new behavior out of it. You need to sort of retrain with perhaps the same large setup, and this gets very expensive very quickly. This is a provably successful way of getting new behaviors from models. So given that context, we'll look at how to look at the third solution, which is interventions at sampling time. In addition to again being more flexible solution to the problem that we are looking at, it is also emerging as the new sort of de facto way in which we are getting solutions that we care about. In particular, especially in like domains that complex domains such as mathematics and the sciences, it is maybe now the de facto standard to get solutions that we care about. I mean, there's a wonderful like blog post by Noam Brown who talks about how the success at tasks that we care about increases with scaling test time compute. Okay, so this is what we want to try to solve. Try to understand how we can get new behaviors from models at using inference time computation. Okay, so just to recall, the abstraction that we care about is that you have a model P and a reward tau, and you want to sample from P tilde, which is the target distribution that we care to sample from. And we want to sample from P tilde without retraining as much as possible, right? This is our setup. Okay, so let's look at the first sort of natural idea that comes to mind when we think about inference time interventions towards solving the problems that we care about. This is in response to the first question that you can ask, which is that how do we have access to both tau and P? So the most natural thing you can do is you have access to your model that you can sample from. Perhaps this is an API, perhaps you have the weights, but the way you'll think about this is that you can press a button and you can sample from these models. And you have query access to tau, which corresponds to being able to verify high reward solutions, being able to verify and check if let's say your output satisfies the constraint that you care about. So I'll refer to this as through this microscope. So roughly the setup in outcome, what is referred to as outcome verification, is just that you are able to sample a bunch of samples from your model and check if the model is high reward, or check if the model satisfies the constraints that you care about. Right, and then after this you are allowed to do whatever post processing you want, and then you output target output that you want to output. right? So this is the setup of what I'm referring to as outcome verification. This is the first sort of maybe the simplest framework where you can work towards like finding solutions to these inference time problems. Okay, so what is the algorithmic solution that that naturally one would think about if this was the only access that you had to the model to the models? And as you might think this is the most natural algorithm one would run is something like rejection sampling. For simplicity, let's just think of tau as being whether your output satisfies some constraint that you can check easily. Like let's say if it's just you want to output code that compiles, and you can very quickly check that whether your code compiles or not, right? That's like the framework you want to work in. And the natural way to run such an algorithm is you'll just sample from your base model and then check if it compiles and just output if it compiles, or just resample if it does not compile. So this algorithm works great. It's a natural sort of like modern extension of an algorithm people have thought about for a long time. Let's say you wanted to sample from this circle, but you only got samples from this square. What you do is you just sample till you got a point in the circle and then output that, and this would work. And this is sort of a modern instantiation of algorithm that people have been thinking about for hundreds of years. So more formally, what you would do is you would sample from P and you would accept with probability proportional to your reward model tau, right? And turns out it's easy to show that this will output a sample from the distribution that you care about. Okay, so there are also related algorithms which maybe we won't think about in the rest of this talk, such as best of n, which would be corresponding to sampling a bunch of samples and outputting the highest reward amongst them. The one minor issue with this algorithm is that it does not sample from the distribution that we care about, and like in applications you might care about what distribution you actually sample from, but this does increase the reward kind of obviously. So this is also a solution to a problem if you just wanted to maximize the reward, but if you wanted to sample from the right distribution, this does not give you the solution that you wanted to sample. So we'll again insist on trying to sample from some target right distribution, but again this still solves some problem. Okay, so but the key issue with both the rejection sampling algorithm and perhaps also best of n is that it depends, naively at least, depends on the likelihood ratio of the target distribution and the original distribution. This roughly corresponds to having your output depend on what the probability your original model outputs a sample that is good under your reward model. In particular, like for example, again going back to the coding example, it would correspond to the probability your base model outputs code that compiles in the beginning. So this could be very small, at least in the worst case. So and the way to think about this really is the issue is that as you increase the horizon of your task, the probability that you're going to output a single solution that is correctly compiles with respect to your reward model gets increasingly small as you increase the horizon length. So one way to think about this again in geometric pictures is that if you have a two-dimensional setting where you want to sample from this circle in 2 dimensions, this will happen with a reasonably high probability. But as you go to higher and higher dimension, turns out that the probability of constraint sets exponentially decays with the horizon length. And in modern applications, we do want to sample from distributions whose horizon goes to increases with increases as much as we possibly can make it. Right? We do care about like super long horizon, super long context reasoning models. So in some sense, this is a fundamental problem with algorithms such as best of n or rejection sampling. Right? So yeah, this is. And especially in problems such as like math, we can really hope to have like sort of super short proofs for problems we care about, but typically as we end up, the proofs are going to be super long and going to take multiple years to worry about. Okay, so the key question is, given that we are increasingly caring about problems where the target is super long horizon reasoning, can we come up with algorithms that are fundamentally better behaved with the horizon length of our problem, and hopefully do not depend exponentially on said horizon length? Right. Okay. So turns out there's a natural solution to think about to solve this problem. The key issue with the reason why this exponential dependence with the horizon came up was because we were only verifying the solution at the end of the entire generation process. That is, we sampled a bunch of tokens, checked if it output the correct answer, and then output this if it did. And if it turns out it's just a fundamental problem of this mode of interaction, there is just nothing we can do that is significantly better than the algorithms that we mentioned earlier. And this again, if you intuitively, this is an issue with long horizon reasoning, and as might be obvious if you think about it for some time, is that if you really want models that are good at long horizon reasoning, we need to be able to provide intermediate guidance for these models, guiding them towards answers that we hope to achieve. So one can think about this as in the frame, it is referred to as process verification, but it's again running a process that is somewhat intuitive, which is you have your model, it's trying to output answers, and somewhere in between this generation process, you want to score your outputs to sort of understand whether this is a good response, or if you can hope the model has a better response for the end distribution that you care about. So an interaction in this setup would be model outputs token. You think, oh, okay, maybe this is a plausible output, and then it outputs the next token, and then you wait it to give it a higher or lower score depending on what it outputs. And at the end of the process, again, you want to output a sample, ideally from the distribution that you care to output from. Right. One again takeaway already is that again, as we are going towards longer and longer horizon reasoning, we need to think about algorithms that interact and guide your models through intermediate processes and at intermediate steps of the reasoning. Okay, so let's try to formalize this and try to understand how to use this framework. Again, recall that we want to sample from P tilde, which just happens to be the distribution multiplied by this reward tau. Okay, so let's say you want to sample the next token at horizon time h, given sort of a partial response y1 to yh for some intermediate time h relative to the horizon t. What would sort of be sufficient to try to understand how we should sample the next token? Turns out again, after a few minutes of thought, the correct object that you need access to be able to sample from this distribution is the conditional probability of the next token conditioned on the output that you have sampled so far. Turns out that the distribution, I mean, one can quickly check by using Bayes rule or Bayes rule that the conditional distribution of P tilde conditioned on y1 to yh is going to be the expected conditional expectation of tau under this conditioning. Right? It sort of intuitively makes sense because the conditional expectation is going to upweight examples that are going to have high rewards while downweighting examples that have low rewards. Right? And it does it in the sort of the consistent manner. So this is the oracle that you want access to. And the ideal process verifier in this framework, or the ideal sort of guiding reward model that you want on partial responses, is just the conditional expectation of conditioning on some partial reward. Right? So this is what you want access to in some ideal world. And it somehow again captures this intuitive notion that we have, is that when you are going through this interactive process of verification, the Okay, I don't know what happened. This is not part of regular programming. Oh, okay, wonderful. Hopefully this will be edited. Okay, let's continue. Yeah, this actually sort of captures the intuitive notion that we care about, which is the object that you want to your guidance to be guided by is sort of some probability of what again some reward model thinks that the next token is going to be given that you have already run some process, right? It's kind of intuitive, and it actually like makes formal what seems plausible, and that's better actually means. It's just a probabilistic way of writing those words more formally, right? So this is what you want access to. And let's say for the next couple of slides, let's just think about having this access to this this conditional expectation explicitly, and let's see what that will lead to. Okay, so the algorithm you would run if you had access to this conditional expectation is the natural one. What you do is for the next token, conditioned on the tokens you have already sampled, you just run something like rejection sampling, or you would upweight the tokens with using the conditional expectation and just sample this going forward. And this algorithm is sometimes referred to as action level rejection sampling, because the action in this setting corresponds to the next token that you can sample. Right, that corresponds to the action that you're taking at each time step. And it's very easy to check by using Bayes' theorem and telescoping that this does indeed sample from the right distribution. So if you did do this repeatedly, if you repeatedly sort of change the next token distribution according to this conditional expectation, it will sample from the distribution that you care about. So this is great, and it runs extremely efficiently because you are there's nothing exponential in Horizon. You're only dealing with tokens at each given time. So there's no exponential dependence on anything. And you can try to sort of run fancier versions of this algorithm, where instead of the next token, you can chunk together tokens and think of blocks of reasoning, and then try to learn a reward model for blocks and so on. And this is consistent with all sort of natural things you would want to do instead of just think of the next token. So yeah, it's a great algorithm. It also only depends on the likelihood ratio for the say the next token or the next action, next block or whatever that you design it, and has again no dependence on exponential Horizon, because the Horizon just does not show up in this algorithm. So this algorithm is great. The only problem with this algorithm, again, if you think about it for 5 minutes, is that it needs access to this conditional expectation exactly. You need, if you had the exact access to this conditional expectation for some reason, this algorithm would output the correct distribution without any issues. But the unfortunate reality is that at least in modern machine learning, all objects that we talk about are outputs of learning processes, and inevitably will have errors corresponding to them. In particular, there is no hope to be able to learn V exactly whatever you think about doing, because it at least depends on this conditional expectation, at least depends on the language model that you have already learned, and you just have no hope of like trying to like output all the probabilities of the language model you have learned. So there are inevitably going to be errors that creep into the processes that into our specification of V. So it is going to be miscalibrated. And perhaps you can hope that the algorithm that we wrote down is robust to misspecifications in a way that that does not sort of again let Horizon creep into our bounds. But turns out that this is not true, and again this is easy to imagine. So as a toy example, let's think about our language model. A model as just outputting something from 3 tokens. It randomly samples A, B or C, and what you care to sample from is on the distribution that does not have any C's in it. One can imagine this is a natural thing you might want to do. Perhaps there's a banned list of words, and you want to not sample from this banned list of words, and C is a banned list in my setting. the present setting, it's easy to check that the conditional expectation, maybe up to normalization, is just the weight of B and C relative to A, B and C, which is 2/3 raised to however much time we have left, and allowing for no C's in the set. This is a math way of saying those things in maybe shorter number of words. And now again, if you, let's say for some reason you upweighted A by an epsilon amount, a small amount, let's say you just thought that A was slightly more likely than B, and you upweighted it by epsilon, then you can just go forward sampling. Then your algorithm would think that A is more likely, should be more likely than B by an epsilon amount, and as you sort of sample this for T steps, you're going to keep accumulating a lot more epsilon times T more A's than B's, and therefore you're sampling from an extremely skewed distribution, and the skew sort of decays with the horizon T. Right, so this is a very clear sort of demonstration of what can go wrong under even mild forms of misspecification. Right, this indicates that there is a fundamental non-robustness to the algorithm that we just talked about, and even under somewhat benign notions of misspecification. Okay. So the key question that hopefully I'll try to address in the rest of the talk, and is the guiding question for this line of research, is that if you're given imperfect verifiers, imperfect reward models, can you sample from the distribution and get the target distribution that you cared about? Okay, so let's try to be a little bit more formal about how we think about this. The one sort of the most simple way in which you can talk about the misspecification is if the ratio between the conditional expectations is off by, say, let's say an epsilon amount, and let's say this holds for all tokens and all sentences, and I'll refer to that as the uniform error condition. Perhaps more naturally in learning settings, you should think about the average version of this, where like for a typical token you have this error, and I'll call that the average error condition. For again the rest of the talk, it suffices to think about the uniform error condition, but everything I say has some analog in the average case as well. It just happens to be significantly more complicated to state and reason about. So the formal question that I'll try to address is that let's say you are given access to a language model P, approximate reward function V hat, and let's say you have access to the original reward tau as well. Can you sample from the distribution you care about, P tilde, and up to some specified error, let's say delta, that is the target that you want to sample from, right? And recall that the natural algorithm, which is just forward sampling or action level rejection sampling, like I said, fails even under the strong uniform condition. Even if I tell you for every sentence that the reward model is only off by an epsilon factor, you would get error that decays, grows with the horizon length T. Right, so there is a fundamental problem with the algorithm, and the question one can ask is if we can solve this issue. Okay, so turns out the answer to this is yes, and in joint work with Dhruv Rohatgi, Yuchen Lee, Donia Salas, Andre Ristevsky and Ankur Moitra, I remember that, I'm impressed. We showed that we can indeed sample from this target distribution under a misspecified reward model, and running in time that is polynomial and reasonably growing with all the parameters that you might care about. So yes.
Polling 1 plus epsilon or polling 1 over epsilon?
It's a way I guess I wrote it. I mean, if you should take logs, and I guess that's the correct thing to look at. 1 plus epsilon is a multiplicative. So as 1 plus epsilon becomes larger, the worse the reward model is.
Okay.
So the way I have written it, 1 plus epsilon is the correct thing. Just think of that as some other constant C or something like that. But yeah. Yeah, it's epsilon is positive.
Okay.
Right, yeah. Okay, so what this theorem is saying in more words is just that, let's say you have a target accuracy delta. Let's think of it as like 0.001, and you have access to a reward model that can be like misspecified. Think of 1 plus epsilon as like 100 or something like that. Then you can sample up to error 0.001 in time that depends again polynomially in the horizon, and log of 0.001, and in polynomial in 100. Right, that's what this theorem is saying. And in particular, the you can get to arbitrarily small target accuracy even if your reward model was arbitrarily misspecified, in at least this uniform notion that we talked about. Right. And like I said before, a somewhat more complicated statement is true under the setting where you had this average case misspecification, where instead of every token your conditional expectation being correct under every sentence, it's correct under some typical sentence, and you'd still get some corresponding theorem with maybe perhaps a more complicated statement. Okay, so again, I won't talk about this that much, but turns out the key way to come up with this algorithm and come up with this theorem is to explore this connection to this area called approximate counting and sampling and Markov chain Monte Carlo. Turns out this is like a rich literature that people have been exploring for the past, again, 50 years, and it's satisfying to see that even in the modern landscape of machine learning, the classical ideas that come from computer science and statistical physics are turn out to be useful. It's just satisfying from that perspective, at least from that perspective. Okay, so in the next few minutes, I'll quickly talk about what the algorithm looks like and how perhaps you can intuit the algorithm. Again, intuitively, what the algorithm really does is tries to do some sort of backtracking, and it's a principled way so that you can implement backtracking. So again, if you thought about this for a few minutes, the natural thing to do is that, let's say you had access to this reward model. What would you, how would you come up with ways of correcting the behavior of the sampling algorithm that you have access to? A natural thing to do is to backtrack. So if you see, you sample forward, if you see some thing that you don't like, you sort of delete these tokens. The key question is, how do you sort of implement this intuitive algorithm in a systematic way that samples from the distribution that you care about? And turns out the solution is, we call this value guided backtracking, and the algorithm is again, in hindsight, super simple. What you do is you have access to this reward model. Just think of the set of all tokens that you can sample from as this big tree, and what the decision that you need to make at each time step is what is the probability with which you will sample the next token, which corresponds to going down this tree, or the probability with which you would delete a token, which corresponds to going up this tree, right? And we need to decide on the probabilities with which you do it. And the idea is that for going down, condition on you decide to go down the tree, you just sample from the greedy sampling algorithm, which is just the forward sampling. You just sample proportional to whatever policy you were doing before, which is P multiplied by V hat. That's again the natural forward sampling algorithm. But just turns out that you have to go back up the tree, you delete a token proportional to the value function at that node. There's this half, let's not worry about that, that's a technicality about lazy Markov chains and such, but let's ignore that for again for the rest of this talk, right? That's the algorithm. Again, all you do is with some probability sample forward, and with some probability again proportional to the value function, you would delete a token, right? This is like sort of a math way of saying that algorithm out loud. This is this procedure. And again, another thing that is satisfying is that it connects a natural idea from classical AI, like AI from the 90s, which is backtracking and like tree search, and connect this to sort of modern algorithmic frameworks such as language models in a systematic way, and comes up with a way in which you can implement this very quickly and very efficiently. In fact, this is like a one-line change to what you would have run anyway. in some sense. So it's a very you can implement this very efficiently given access to these procedures, right? So this is another reason why this is very satisfying, at least to me. And again, I'll spend the next like a couple of minutes trying to say why this algorithm works and what does the analysis entail, but this is going to be super quick. The key idea is, again, if we have seen analysis of Markov chains before, the key idea is to set up a Markov chain whose stationary distribution is the distribution that you care about. And it's not that hard to check that this distribution indeed has the correct stationary distribution. The real reason is because this is a tree, and at the leaves you can actually check the answer correctly, and there's just nowhere else for the mass to go. So this just has to sample from the right distribution. And another satisfying part of this theorem is that, again, it relates ways we think about, again, Markov chains, which happens to be this notion called conductance, to the error of the reward model that you have. So in some sense, it relates how you would analyze running times of algorithms to errors of oracles that you have. It's again a satisfying property to have. The turns out the average case analysis is which is a more realistic version, involves modern techniques in local stationarity and slow mixing Markov chains. We don't have to worry about that too much, but it's an interesting line of thought that is being explored recently. And overall, the whole analysis connects average case analysis to Markov chain mixing times. Okay, so I spoke so much about theoretical evidence. There are like toy tasks where people ask for which benchmark algorithms of this sort, and in all of these algorithms, relative to, again, the benchmarks that we at least quickly spoke about, turns out these algorithms outperform the benchmarks sort of significantly, at least in these toy tasks. And there are several other examples which are a little bit, there's a robust set of experiments in the paper, and I encourage you to look at it if you're interested. Okay, in the last few minutes of my talk, I want to leave you with sort of a broader overview of where this research direction is going and what we expect from this, at least in the next few years. So there's been an active line of work trying to expand this line of work, trying to understand what we can do at Inference-time. And people have been using what are called particle-based methods, which corresponds to, again, having a bunch of different parallel trajectories of your language model and try to sort of understand the relative quality of these different trajectories, and trying to decide which ones to keep and which ones to curb. Again, turns out this is very closely related to ideas from physics and ideas from sampling, and roughly they are referred to as like particle-based methods. And it's again satisfying to see that these ideas come back in this modern light. The versions have also been generalized for from language models to mass diffusion models and diffusion models more generally. So in particular, it's super satisfying again to see this recent extension of the algorithm that I mentioned to the setup of mass diffusion models, where the algorithm again looks roughly the same way. This is actually illustration from their paper. It's super nice. As you go from left to right, you have high reward, and what this is trying to indicate is how you could try to search for a high reward element in this tree using these algorithms. This is a nice illustration. Further, it turns out this has been applied to problems that they happen to care about, such as protein synthesis and DNA and so on, and some problem solving, and turns out it does better than corresponding benchmarks in those setups. So it's super satisfying to see how these algorithms have real world applications. And yeah, I mean, for a more sort of thorough look at the landscape and try to, if you're interested, you should look at this tutorial we had at this conference a couple months ago with Sitan Chen, Noah Golovich, and Dhruv Rohatgi. Okay, so I'd like to sort of end this talk by just having us sort of think about how the following important aspect of how we train models. It is important to sort of think about our training procedure for both our reward models and our language models generally should be dictated by what we can do with them and the what algorithmic primitives that you can implement on top of the sampling procedures. And this is particularly interesting because the landscape of what you can do at inference time is particularly rich, and one should be cognizant of like how one trains their models given how you are going to use them at inference time. And this interplay between the algorithmic landscape at inference time and how we train our models should be very active because the landscape is extremely rich. So it's a worthwhile exercise to think about how we train our models, given that we are going to be using them at like in increasingly sophisticated ways. Further, I genuinely believe, and it's maybe perhaps obvious, that inference time computation can unlock truly long horizon behavior if you use computational aspects and reward models in a robust way, and we should be cognizant of this fact and think about how we again train and use our reward models and language models to unlock capabilities that we want from these models. So I'm happy to take any questions, and thanks so much for your attention.